We're ready to get started. Make sure for me that you have your mic muted and go ahead and turn off your camera, and that'll make the system run a whole lot better for us. And today we are recording this session, and we'll have the video posted on the A+ College Ready YouTube channel here this afternoon. The PowerPoint that I'm using, I'll send out to teachers later today. We have one more of these sessions coming up, and it will be on on May 13th at 11. Notice that time is different than it normally is. It's at 11 instead of 2 that day. Also realize that your exam is the next day. That's May 14th at 3 o'clock, and that is 3 o'clock Central Time. So we're getting close. 1 week from today, actually, 1 week from tomorrow, rather, is your exam. So getting really close. Today we're going to talk about a topic that we haven't talked about at all in these sessions, and that is simple harmonic motion. And it's a topic you may or may not have gotten to before all this craziness broke out. So simple harmonic motion is a type of periodic motion. So it's sort of a vibrational kind of motion. We might say it's oscillatory. That is something that oscillates back and forth. During this type of motion, periodic motion, there's one point in the object's path where there's a net force of 0. Therefore, an acceleration of 0. That's equilibrium. That's called the equilibrium position. When the object is pulled away from that equilibrium position in either direction, there's a net force that's not 0. And that net force always pulls or pushes the object back toward the equilibrium position. It accelerates it back toward the equilibrium position. So here's the definition of simple harmonic motion. If that force, that restoring force that we talked about a minute ago, is directly proportional to the displacement of the object away from equilibrium, the motion we get is called simple harmonic motion. So it's only simple harmonic motion, or you'll see it simple harmonic motion abbreviated SHM. It's only simple harmonic motion if the restoring force is proportional to the displacement away from equilibrium. And remember, that force is called the restoring force because it's always trying to restore that object back to the equilibrium position. Because the net force, the restoring force, is proportional to displacement, that means the acceleration is also always proportional to the displacement. And it's always toward the equilibrium position. When we're talking about simple harmonic motion, there's some important terms to be aware of. Period, abbreviated capital T, is the time required for one complete cycle. And the amplitude, abbreviated capital A, is the maximum displacement away from the equilibrium position. That could be on either side of the equilibrium position, but it's the maximum displacement away from equilibrium. So something related is Hooke's law. So Hooke's law deals with the restoring force. And it essentially says that the restoring force in a spring is proportional to the length the spring is stretched. It also says that restoring force always acts in the opposite direction of the displacement, always trying to take that spring back to equilibrium. What that means is the bigger the force that's used to move the object, the more it will stretch. This is Hooke's law. F equals K, negative K times X, where F is the restoring force. K is something called the spring. Sometimes it's called the force constant. It's specific to each spring. And essentially it relates how much force there is per unit of compression or stretching. X is the amount of displacement away from equilibrium. Now you notice that negative sign in the equation. That negative sign is there because the force is always in the opposite direction of the displacement. K is always going to be a positive number. So if X is negative, that tells you the force is going to be positive. On the other hand, if X is positive, that tells you the force is going to be negative. Those are always going to be in opposite directions. So Hooke's law, the equation for the restoring force of a spring, and it's equal to negative spring constant times displacement away from equilibrium position. So let's look at a quick problem for how we might deal with this. So we've got a spring attached to a ceiling. So let's say this is the ceiling right here, and here's our spring. And it's got a block attached to it. Here's our block. The block has a mass of 3 kilograms. We're on Earth right now. The displacement of the spring when at equilibrium is 0.3 meters. So when we hook the block onto the spring, it stretches the block an additional 0.3 meters. What's the value of the spring constant? Well, remember that F equals negative kx. So the force here is going to be the weight of the block. So we're going to go 3 times 10 to get the weight of that block, 30. Let's solve this out for k. So we're going to divide both sides by x. And we could also multiply both sides by -1 if we wanted to. Not so important here, though. So our k is going to be equal to the force, 30 newtons, the weight of the block, divided by the displacement caused by that, 0.3 meters. So if we divide our 30 by our 0.3, we end up with 100. And notice that the units on this are 100 newtons per meter. K is always going to be measured in newtons per meter, at least in this class. So part B, what is the displacement of the spring at equilibrium if the system is moved to a planet with an acceleration due to gravity of 4 meters per second square? So now we take this thing to a different planet. It's the same spring, the same mass. This time we want to know the displacement. So we're still going to use Hooke's law. This time we're going to divide it by, we're going to solve it for x. So we'll divide both sides by negative k. We'll put in the force. This time the force is going to be the weight of that object, which is going to be 3 times 4. Mass times acceleration due to gravity. So that's going to be 12 newtons. And we're going to divide that by the spring constant, which is 100 newtons per meter. Notice newtons cancel. And we're going to end up with a displacement of 0.12 meters. And it's negative 0.12 meters because it's going down. That's why the negative sign is there. All right, so simple problem dealing with mass on a vertical spring. We'll come back to those in a minute. Before we do, let's talk about some other examples of simple harmonic motion. So these can work with masses on vertical springs. It can work with masses on horizontal springs. Now that's only if we ignore friction. It can also work with pendulums. We'll talk about pendulums more in a minute. When we're dealing with masses, we oftentimes on springs, we want to talk about elastic potential energy. The elastic potential energy in a spring can be calculated with this equation, where the elastic potential energy is equal to 1/2 times the spring constant times the displacement squared. We also can calculate the period of a mass. And this is the equation for the period. So here the T is not tension, it's period. 2 pi times the square root of the mass of the object over the spring constant. We'll come back to that equation more here in a minute. One other thing we can calculate if we need to know the position of the object at a specific time, we can multiply the amplitude, that's the maximum displacement, times the cosine of the quantity 2 pi times frequency times time. And that will give us the position of the object at a particular point in time. All right, so let's look at this picture right here. So here we're dealing with a mass on a horizontal spring. And you can see the equilibrium position marked in blue. So let's say that we took this mass and we stretched it back this way. And we stretched it to a maximum displacement of A. So the distance from here to here is A. That's the maximum displacement. Right now, we're still holding on to it. The velocity at this point is 0. But the acceleration is at a maximum. If we let this thing go, as soon as we let it go, the displacement is as at a maximum. And remember, the restoring force is proportional to the displacement. So if the displacement is at a maximum, the restoring force is at a maximum. And the closer that thing inches back to the equilibrium position, the less the restoring force is going to be, and therefore the less the acceleration is going to be. So we could say that at this maximum displacement, the restoring force is also at a maximum. As we let it go, the object moves back. It goes back toward equilibrium. When it gets to the equilibrium point, its displacement is 0. By the time it gets back to equilibrium, it has accelerated up to its maximum velocity. It's going as fast as it will ever go at this equilibrium position. At this instant in time, there's no restoring force because the spring is at its equilibrium position. So the restoring force is 0, and because there's no net force acting on that object, the acceleration is also 0. Now that doesn't mean this box stops moving because it's got inertia. So the box continues to move. And now it starts to bunch up, compress the spring. So now the displacement is this way, which means the restoring force is going to be this way. And as that displacement gets bigger and bigger and bigger, the restoring force gets bigger and bigger and bigger, and the acceleration gets bigger and bigger and bigger. So eventually the box gets back to its maximum displacement, its amplitude. Notice in this case, the displacement is negative amplitude. So that's here. At that point, it stops moving for an instant. So the velocity at that point is 0. Also at that point, the restoring force is at a maximum. It's pushing this way. And the acceleration is also at a maximum. It's also pushing that way. Remember, the restoring force and the acceleration are always pointing toward the equilibrium position. Doesn't matter which side of that equilibrium line you're on, the restoring force and the acceleration are always going to be acting toward equilibrium position. All right, sometimes they like to throw position time curves at you for simple harmonic motion. So let's think about this thing. So here we're saying that the box, and let's just draw a quick drawing here. Let's say here's our spring, and here's our box, and here's equilibrium. So if we stretch the box, and actually let's start off this way. So let's say we pull the spring this way, and we stretch it out to maximum displacement over here. That's where we're at this point. When we let it go, it's going to start moving back toward equilibrium. Notice at this point A, we're far away from the equilibrium position of 0. Now it starts to shoot back toward that equilibrium position. So the position goes down. Here the position gets to 0. So at this point, the box is back here. It's back at the equilibrium position. But remember, it doesn't stop because of its inertia. So it continues going this way. And as it goes, the spring is going to compress. And the restoring force is going to be pushing it back this way. The acceleration is going to be acting this way. And we can see that eventually it stops. It gets to the maximum negative amplitude, which would be over here somewhere. At that point, the spring starts pushing it in the other direction, starts pushing it up. So now it starts shooting back this way. It shoots back through its equilibrium position right there, continues going toward the right until it gets over here to its maximum amplitude. And that's where we started. So from this point on, it just starts over again. It starts from here to here. Here it starts over yet again. Anytime it crosses the x-axis, that's when the box is at the equilibrium position. Anytime it maxes out down here, we might call these minimums and these maximums. Anytime we get to the peaks or the valleys, we're talking about the box being at its maximum amplitude, its maximum displacement. All right, so let's look at an example problem. Everybody take just a minute and read that problem. All right, so we're starting out with a mass on a spring. It's on a table or something. And in this case, the spring is stretched this way, 25.53 meters. So that's the maximum displacement. And then it's released. Find the mechanical energy of the system. Well, I'm hoping you guys remember that mechanical energy is the sum of the potential energy and the kinetic energy. So mechanical energy is equal to the potential plus the kinetic. Well, when this thing is stretched over here to its maximum displacement, it's not moving. All it has is elastic potential energy. All of its mechanical energy is its elastic potential energy. There's no kinetic. It's not moving at that point. So at this point, at maximum amplitude, all of the energy, all of the mechanical energy of this system is elastic potential. And we can calculate how much elastic potential energy there is using the equation elastic potential energy equals 1/2 K times x squared. In this case, that is 1/2 times our spring constant of 78 newtons per meter times our displacement, which is 25.53 centimeters. Since K is always going to be in newtons per meter, you want your displacements to be in meters as well. So we need to do that as 0.2553 meters. Just divided by 100 to convert from centimeters to meters. Don't forget to square that. It's 1/2 kx squared. So when we multiply that out, we end up with a elastic potential energy of 2.54 joules. And that's our answer on part A. All right, so now we're ready to work on part B. Find the speed of the mass when it has moved to 3.63 centimeters from the equilibrium position. So now it starts to shoot back this way. And now instead of being 25.53 away from equilibrium, it's only 3.63. Here's what you got to be careful of. Remember that as the box moves back toward equilibrium, the force, the restoring force, and the acceleration decrease, and they decrease pretty drastically. So here's what we need to do. Because we know the 3.63 centimeters, we can calculate how much elastic potential energy there is at that point in the box. And we can use elastic potential energy equals 1/2 kx squared. So that's 1/2 times 78 newtons per meter times, we got to convert that to meters from centimeters. So 0.0363 meters. We do the math on that, and don't forget to square it. It's 1/2 kx squared. The amount of elastic potential energy comes out to be 0.0514. And that's joules, 0.0514 joules. Now, here's the important point. We know that the total mechanical energy at the beginning of this problem was 2.54 joules. When the box is moved to this point, there is 0.514 of those joules that are, and by the way, this is mechanical. Remember that mechanical is equal to potential plus kinetic. So our total mechanical energy is 2.54. At this point, 3.63 centimeters from equilibrium, 0.0514 joules are elastic potential. That means the rest has to be kinetic. So let's subtract 0.0514 from the total of 2.54 and end up with a total amount of kinetic energy of 2.4886. Now what you got to remember is that kinetic energy is equal to 1/2 mv squared. We're trying to solve here for the speed. So let's solve this for v. So let's multiply both sides by 2. Let's divide both sides by mass. And then let's take the square root of both sides. And when we do that, we end up with a speed of the square root of 2k over m. We would plug in our 78 right here for k. We would plug in our 0.766 right here for mass, solve that out, and we end up with a speed of 2.55 meters per second. And that's always back toward the equilibrium position. The last part of this question asks us to find the maximum speed. Well, remember, the maximum speed is always going to be at the equilibrium position. It's when all of the mechanical energy is in the form of kinetic energy. Which means, if we go back to this equation here, we had 2.54 joules of total mechanical energy. When it's at its maximum speed, 0 of that is elastic potential, which means all of that has to be kinetic. So if we take the 2.54 joules, all of it, and set that equal to the kinetic energy equation, remember, K equals 1/2 mv squared. We determined we have 2.54 joules of kinetic energy. That's equal to 1/2 times the mass of 0.776 times the speed squared. Let's solve that out for speed. And when we do, we end up with a speed of 2.58 meters per second. Notice that that speed is not a whole lot faster than the speed was when the thing was still 3.63 centimeters from equilibrium. And that's because the restoring force had greatly decreased and the acceleration had greatly decreased as the object got closer and closer to equilibrium. All right, I'm going to stop there for a second and take questions. Does anyone have questions on this first problem? All right, well, here's the second problem. Same kind of thing. So here we have another mass on a horizontal spring. Notice it gives us the mass is 0.0750 kilograms. Tells us the spring constant is 400 newtons per meter. And we want to know the maximum speed of the block if the amplitude is 6 centimeters. Assume the spring is an ideal spring. So we're saying we don't have any friction or anything like that. So first of all, we need to figure out how much mechanical energy our system has. And remember that at maximum amplitude, all of the mechanical energy of the system is elastic potential. So let's use our elastic potential energy equation. 1/2 kx squared. Take 1/2 times k, 400 newtons per meter. Multiply that by the maximum displacement, which is 6 centimeters, 0.06 meters squared. All right, if we multiply that out, we end up with a total total elastic potential energy of 0.720. And that's joules. That's the elastic potential at maximum displacement, which is also the total mechanical energy of the system. Now, what we're trying to find in part A is the maximum speed. So at this point, all of our energy is elastic potential. But now the restoring force pulls this thing back. It accelerates back toward equilibrium. And at this point, the equilibrium position, all of that mechanical energy is now kinetic energy. So we're going to set K equals 1/2 mv squared. All of our energy at this equilibrium position is going to be elastic potential energy. All of our energy, all of our mechanical energy at equilibrium is in the form of kinetic energy. That's always where the maximum speed happens, at the equilibrium position. So we're going to set 0.720 joules, all of our energy, equal to 1/2 times the mass, 0.0750 kilograms, times v squared. We would do the algebra and solve this out for v. And when we do, we came up with a speed of 4.38 meters per second. So that's the speed right here at the equilibrium position. All right, now B. What is the speed of the oscillator when it is located 3 centimeters to the right of the equilibrium position? Assume the amplitude of the oscillations is still 6 centimeters. This is where a lot of you would fall for a trap, and you would think, well, okay, at 6 centimeters, the spring was storing this much energy. So at 3 centimeters, it should be storing half of that much energy, 0.360 joules of elastic potential. And if you did that, you would be wrong, because what you've got to remember is that the force is not constant. The force decreases as the mass moves back toward equilibrium. The acceleration is not constant. The acceleration decreases as the mass moves back toward equilibrium. So what we've got to do to work a problem like this one is to calculate how much elastic potential this mass has at the 3 centimeter mark. So we'll use our elastic potential energy equation. 1/2 kx squared. We'll take 1/2 times k, 400. We need to convert that 3 centimeters to meters, so 0.03 meters squared. Do the math on that, and we end up with an elastic potential energy on that one of 0.18. Well, remember, the thing had a total energy of 0.72. So that means if 0.18 of it is elastic potential, the rest of it is kinetic. So subtract that out, 0.72 minus 0.18. We end up with a value of kinetic energy at that point, the 3 centimeter mark, of 0.54 joules. We need to set that equal to 1/2 mv squared, and then we can solve for speed. So we'd say 0.54 equals 1/2 times the mass times v squared. Do the algebra, solve for v. We end up with a speed at the 3 centimeter mark of 3.79 meters per second. So again, not a whole lot less than the maximum speed. Max speed was 4.38. By the time we get halfway there, we're already to 3.79 meters per second. All right, let's go ahead and answer C. And we've kind of already answered C. What is the total mechanical energy of the system? And remember, the easiest way to find that is either number one, if you already know the speed at equilibrium, you can calculate kinetic energy, 1/2 mv squared. In most of these problems, though, they give you the maximum displacement, and probably they're going to give you K. So the easiest way is to calculate the elastic potential at the maximum displacement. At that point, all of the mechanical energy is elastic potential. So we calculated that out to be 0.720 joules. And that is true at maximum displacement. So it's true here. It's also true here. And it's also true here. At this point, all of that energy is kinetic. At this point, it's all elastic potential. At this point, it's also all elastic potential. All right, D wants us to find the period of this oscillator. So remember, I showed you an equation a second ago. The period of a mass on a horizontal spring is 2 pi times the square root of mass over spring constant. So the only things that determine the period of this thing, the mass of the object and the stiffness of the spring, essentially, the spring constant. So in this case, it would be T equals 2 pi times the square root of 0.0750 kilograms over 400 newtons per meter. If we do everything in terms of newtons, meters, and kilograms, our period, once we calculate, is going to come out in seconds. So let's do the calculations. 0.05 divided by 400. Take the square root of that whole quantity and then multiply by 2 pi to end up with a period of 0.0860. Finally, this thing asks us for the frequency. And remember, essentially the frequency tells us how many cycles there are per second. In this case, how many times does this thing go back and forth each second? You need to remember that frequency is equal to 1 over the period, and that period is equal to 1 over the frequency. Since we have the period, our frequency is simply 1 over that. So it's easiest just to go ahead and divide that out. 1 divided by 0.0860, and that gives us 11.6. Now, what your units are going to be on that? You could write it as something like that per second. You could write 11.6 s to the minus 1, or you could write 11.6 hertz, which is another way of saying how many things happen per second. Any of those units will work. Over seconds, s to the minus 1, or hertz. All right, we'll stop there. Take questions if anybody has any questions on this one. All right, moving on. But now let's look at a mass on a vertical spring. All right, so in this case, we're starting out with a spring and a mass. It's at equilibrium. We stretch the spring, so we pull down on it. We pull it to a maximum displacement. At this point, the restoring force is up. The velocity is 0 because right now we're still holding on to it. It's not moving, so it has a kinetic energy of 0. It has a potential energy or elastic potential energy max. It's also going to have an acceleration of max at that point, because when we let it go, it's going to shoot up very quickly. As it gets closer and closer to equilibrium, the restoring force decreases, the acceleration decreases. Here it's at equilibrium. At equilibrium, remember, that's when the velocity is a maximum. The net force at that point is 0. The acceleration at that point is 0. Because the velocity is at a max, the kinetic energy is also at a max. And the potential energy, the elastic potential energy, is 0 because the spring is not stretched or compressed at that point. But remember, the box doesn't stop there. It continues up because of its own inertia, and it compresses the spring. And it continues to compress and compress until that box gets to a maximum displacement. At that point, it stops moving, so the velocity is 0. Also, at that maximum displacement, the restoring force, the net force, is at a maximum. It's pointing always back toward equilibrium. The acceleration at that point is also always going to be at a max. 0 kinetic energy because at the time it stopped, and the elastic potential energy is at a max because the spring is compressed as far as it can be compressed. All right, so once it stops, now it reverses direction, heads back toward equilibrium, gets back at equilibrium. Again, at that point, velocity is at a max. Because of that, kinetic energy is at a max. Because it's at equilibrium, there's no net force. Acceleration 0. And because the spring isn't stretched or compressed, the potential energy is also 0. And at that point, we just start over again, back and forth, following the same periodic motion. So here's another example of a vertical spring problem. So in this case, we have a 0.25 kilogram mass. We attach it to a spring. It stretches the spring 0.52 meters. The system is then placed horizontally on a frictionless surface and is set into simple harmonic motion. What is the period of the oscillations? So here we're in the vertical part of this problem. And what we can do is we can use the force, because what's going to happen is the spring is going to stretch down. And when it stretches down to its maximum and stops, at that point, the weight of the object is balanced out by the restoring force up. So those two are equal. So if we know the weight at that point, we also know the restoring force. So let's find the weight. The weight's going to be the mass, 0.25, times acceleration due to gravity, 10. So our weight, which is going to be our restoring force, is equal to 2.5 newtons. Mass times gravity. Now we can go to Hooke's law. F equals negative kx. Solve that out for k. So k is going to be equal to F over x. The negative sign doesn't really matter so much here. It's really a directional thing. So the force is going to be our 2.5 newtons. And our x is going to be our displacement, 0.052 meters. We do the math on that. We end up with 48.1 newtons per meter for K. All right, so now we take that same box, same spring, and now we put them on a horizontal table. So something like this. So here's our spring, here's our box, and we want to know what's the period of these oscillations. We've got to think back to the equation for the period of a mass on a spring, and that is 2 pi times the square root of m over k. We know the mass. The mass of our object is 0.25 kilograms, and we just calculated k. K is 48.1 newtons per meter. And remember, if you do all your math in kilograms, newtons, and meters, your period's going to come out in seconds. So 0.25 divided by 41.8, take the square root of the quantity, and then multiply by 2 pi. You end up with a period of 0.453 seconds. All right. So now we're ready to do one more problem, and this time we want to talk about pendulums. So here's a simple pendulum. Some things you ought to know about the pendulum. Number one, this is the equation for the period of the pendulum. You'll find this equation on your AP Physics 1 formula sheet. Notice that the only two things that affect the period of a pendulum are the length of the pendulum and the acceleration due to gravity. The mass doesn't matter. The angle that the pendulum is moved away from equilibrium doesn't matter. The things that determine the period of the pendulum are the length and the acceleration due to gravity only. Another thing you're going to want to do is to be able to calculate the restoring force that acts on the pendulum bob and also the tension, the amount of tension that acts on the object. And to do that, you want to come in and draw a force diagram. So you're going to draw down, this is going to always be your weight. We know that weight, or mg, always acts straight down. You then take that weight and divide it into components. So in this way, in this case, you're going to divide it into one component that acts along the string. That component is going to be your tension force. And then you're going to divide it into another component that acts perpendicular to that tension and back toward equilibrium. Notice that's a 90-degree angle right there. This component is going to be your restoring force. So if we did a little math here, and notice that this angle between all those, between all these lines, the tension, the weight, and the restoring force, the angle between the weight and the tension is going to be the same as the angle of displacement of your string away from the equilibrium position. So if we wanted to calculate the restoring force, we could use sine. And we could say the sine of theta is equal to the opposite side, which is our restoring force, over our hypotenuse, which is our weight, mg. If we solve that out, the restoring force is equal to mg sine theta. We could do the same thing with our tension. The tension is the adjacent side of that angle. So we could use cosine. And we could say cosine of theta equals adjacent side, tension, over hypotenuse, mg. So tension is equal to mg cosine theta. Now don't confuse this t. This t is tension. This t is period. So sometimes it might be better to write F of t for tension, force of tension. Keep those equations in mind. Let's look at this next problem. For simple displacements, small angles, angles less than 15 degrees, a pendulum is a simple harmonic oscillator. We're assuming that when we do that, that the cord doesn't stretch and that the mass of the string is small enough that we can ignore it. So those may not always be true, but the back and forth motion of this pendulum pretty much is simple harmonic motion. The restoring force is proportional to the displacement away from the equilibrium position. That's the definition of restoring force. It can be calculated mg sine theta, and the tension in the rope or the cord is mg cosine theta. Keeping that in mind, let's look at a problem. Before we do, remember that's the equation for period. It's reliant on length of string and acceleration due to gravity only. Here's the problem we want to look at. So we've got a pendulum bob. That's a little mass at the end of the pendulum. That's 2.02 kilograms. And we're displacing the bob from equilibrium by 10 degrees. So this angle, 10 degrees. Draw a free body diagram to show the forces that act on the bob. Remember that when you're doing free body diagrams, you don't show components. So if this is our bob, the only forces acting on this bob are number one, weight, which always acts straight down. So we could label this as weight. We could label it as F of G, the force of gravity. We could label it as mg. Any of those would work. The only other force acting on this bob is the tension force. And that tension force is acting along the string. Maybe something like that. And let's notate that as F of T, force of tension. Next thing, what's the magnitude of the restoring force? So again, go back to the picture for a second. And let's just do it on this picture. when we want to calculate the restoring force, first of all, draw in your weight straight down. That's mg. You want to break that into a component along the string and a component perpendicular to that acts back toward equilibrium. This component along the string is the tension force, and this component is the restoring force. This angle right here is always the same as this angle right here. So if we want to calculate the restoring force, we're going to use sine. And in this case, it would be the sine of 10 degrees is equal to the restoring force, opposite side, over the hypotenuse, mg. Well, mg is going to be 2.02 times acceleration due to gravity of 10. So that's 20.2 newtons. Multiply both sides of that by 20.2. And we end up with a restoring force of 3.51. And that restoring force always acts back toward the equilibrium position. Same kind of logic to do the tension in part C. Remember that the tension component of this picture is right here. We're going to use cosine to find the tension component. We're going to say the cosine of 10 is equal to the adjacent side, which is the tension, over the hypotenuse, which is mg, 2.02 times 10. Solve that out, 20.2 times cosine 10. And we end up with a tension in the string of around 19.9 newtons. Next, we want to know if the length of the pendulum cord is 52 centimeters, what's the period? So think back to that period equation we had on the screen a minute ago. The things that determine the period of a pendulum are length and acceleration due to gravity. 2 pi times the square root of L over G. So it's, in this case, it's going to be 2 pi times the square root of, notice this is in centimeters. We need that length to be in meters. And the reason we need it to be in meters is that our acceleration due to gravity is in terms of meters. So let's divide 0.52 by 10, take the square root of that whole quantity, and then multiply by 2 pi to end up with a period of 1.43 seconds. So that's the time it takes this thing to go from this point all the way over here and then back, over, back, over, back. Each over, back time frame is 1.43 seconds. Last part of the problem wants us to find the frequency. Remember that frequency is 1 over period. So in this case, it's going to be 1 over 1.43. Divide that out. We end up with a frequency of 0.699, 0.699. And remember, we could write that as per second like that. We could write it as 0.699 s to the minus 1, or we could write it as 0.699 hertz or cycles per second. All right, that's it for our simple harmonic motion problems for today. Are there questions?